Sir, noon time or during the daytime, almost the entire sky is blue in color. During the sunset and sunrise, it is red orangish. Sir, suppose one particular room full of dust, nobody is using that. One window alone opened, through that window, sunlight is entering. First part we have discussed reflection and refraction. Second part we are going to talk about total internal reflection and about lenses, convex lens, concave lens, and we are going to talk about a simple concept known as dispersion of light. Total internal reflection. Sir, for total internal reflection to occur, two conditions it should satisfy. First condition, light should be refracted from denser medium to rarer medium. Denser to rarer, it should refract. First condition. Second condition, angle of incidence should be greater than critical angle. What is the meaning, sir? What is called angle of incidence? I see. What is the meaning? Sir, we have a medium. This is air. This is denser. Air, denser. Air, denser. Now, denser to rarer, it should refract. That is a condition. So, allow one radiation. This is called angle of incidence. Already we have studied denser to rarer means light bends away from the normal. Rarer to denser means towards the normal. In refraction basics we have seen. So this is denser to rarer. I, this should be R. Next, what you are doing is you are increasing the angle of incidence. I is equal to IC. Angle of incidence, IC, we call it as critical angle. Critical angle. So after refraction, it grazes the surface. Grazes means R is equal to 90. At critical angle, the refracted ray is perpendicular to the normal surface. No, sir. I want to increase greater than I, greater than I. The incident light angle or representation is greater than the critical angle. At that moment, no refraction at all. The entire light will be reflected. There is no refraction concept here. Correct, Amma? Simple concept. Total internal reflection. We have some applications for total internal reflection. Glittering of diamond. Optical fiber. Examples for total internal reflection. In detail, next part we will do. Okay, sir, you told light means it is capable of reflecting, refracting, total internal reflection, all these things. Then what are the major parts, major properties of light? There is no question of property here. The velocity of light is 3 into 10 power 8 meter per second. Light is a form of energy. Light is a form of energy. No medium necessary for transformation. It can travel in vacuum itself. No medium necessary at all. Since it is a wave, it cannot be deflected by electric and magnetic field. It is a wave. Important thing here is dispersion. There 1 or 2 points extra we will study. Sir, you consider a prism ABC. This is incident light. White ray. Incident. This is screen. Light is incident, refracted. Light is incident, refracted. Why you are putting two rays, sir? White light is a combination of 7 colors. VIBGR, violet, indigo, blue, green, yellow, orange, red. 7 colors. Correct, Amma? So, violet is the most deviated ray. This is delta V, violet. Red ray, delta R. Least deviated. Why violet is getting deviated more? Why red ray is deviated less? Simple. Already we have seen the formula. C is equal to, of course, one formula here. C is equal to nu lambda. Velocity is equal to frequency into wavelength. We have a formula in this. So C is equal to nu lambda. Violet, red. Frequency remains the same. Any light, when it travels from one medium to another medium, frequency remains constant. Velocity will change, wavelength will change, frequency will not change. So, here speed of violet ray is less. Why less? Lambda is less. Lambda is less for violet. 4,000 Armstrong unit. 4,000 Armstrong unit lambda. Around 4,000. Red ray around 7,000 Armstrong unit. So lambda is 4,000 means velocity is also less. Here lambda is 7,000. So velocity is also more. Frequency, both the cases same. So because of that lesser speed only, when it comes through the prism will deviate more because velocity is lesser. So most deviated. Red ray, when it approaches, it splits into 7 color. It is not 2 ray alone. Between violet and red, indigo, blue, green, yellow, orange, red, everything is there. Extreme colors we have taken, that's all. Extreme colors. Correct, Amma? Simple concept. Rayleigh's scattering law. Other than reflection and refraction, we have a new term known as scattering. Amount of scattering is inversely proportional to 1 by lambda power 4. It's called Rayleigh scattering. Sir, noon time or during the daytime, almost the entire sky is blue in color. During the sunset and sunrise, it is red orangish. Around 4:30 it becomes yellow. Then around 5:30 it becomes orange. Around 6 to 6:15. This is all winter season. Closer to the sun, it appears red. So yellow, orange, red. As time increases, yellow, orange, red. Okay. Why sky appears blue in color means lambda is less for that. Sir, this is earth. This is sun. At the known time, the distance between earth and sun is small. Lambda is nothing but distance between two consecutive crust or two consecutive trough, two consecutive compression, two consecutive rarefaction. It is a distance. Okay, so lambda is less. When you say lambda is less, amount of scattering will be enormously high. Entire sky becomes blue in color. During sunset or sunrise, nearer to the sun, it is reddish, yellowish, orangish like that and all. Suppose this is sunset, sunrise. See, this is observer. Observer here. For him, the distance is small. But for him, this distance is more. Here also it is more. So distance is more means lambda is more. Lambda more means amount of scattering is less. So violet ray, indigo, blue and all will scatter away some more distances. Only these three combination. Yellow, orange, red. That combination only will get. Raman effect. Tyndall effect. Sir, what is called the Raman effect? Sir C.V. Raman, the great scientist, awarded Nobel Prize for his effort. Whenever light enters through a pure liquid or pure transparent solid, light splits up into three categories. Why three categories? Only one should come. Initially, original ray. In addition to that, two more extra rays are coming. One is called the Stokes line, another is called the anti-Stokes line. So when light is incident on a monochromatic light, of course, incident on a solid means transparent solid, pure liquid, involves three different lines. First one, original. Second one, Stokes line. Third one, anti-Stokes line. Higher classes, we will discuss what is the meaning. Tyndall effect. Tyndall effect means, sir, suppose one particular room full of dust, nobody is using that. One window alone opened, through that window, sunlight is entering. When sunlight is coming, that path you can see so many dust particles of the room. Then the path is not visible. You can see the sunlight path. Correct, Amma? Simple. Similarly, colloidal particles. Scattering of light by colloidal particles. Scattering of light by dust particles. This we call it as Tyndall effect. Next, lenses. Convex lens, concave lens. Sir, this is convex. Correctly speaking, this is biconvex lens. Biconvex. This is concave lens. Convex lens, concave lens. Curved out, we call it as convex. Curved in, we call it as concave. Similar, what we have studied in mirror. This is principal axis. Most of the places they have put only P, but one or two places they have put this as C. This is known as optic center. Now pole will not come, mirror alone pole. So this pole will be replaced by optic center. Clear? F, light is incident. Any ray passing parallel to principal axis after refraction pass through the focus. Thereafter reflection we saw. Here we are seeing refraction. Next, this is F, this is 2F. Now you are placing the object at in beyond 2F. Beyond 2F. Where will you get after reflection? Between, there is no question of reflection here. It is refraction. So same thing what we have studied for a mirror, we have for a lens. Concave mirror property and convex lens property, both are almost same. Correct, Amma? Good. Next important topic, here you're going to see lens maker's formula. Lens maker's formula and lens formula. Lens maker. Lens manufacturer's formula. 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. This is a formula for lens maker. F is the focal length of the given lens. What is that value? Use this formula, mu, that lens refractive index. What is the radius of curvature of the first surface? This is radius. So this one, this is only a part of a sphere. When you extend that one, this is called radius of curvature. This is also part of a sphere. Okay. Now, this distance from this center to this center, radius of curvature, R1. That side, R2. Two spherical surfaces combined to form a lens. Simple. Power of a lens. Power is 1 by focal length, 1 by meter or meter power minus 1. Sometimes we'll use as diopter. Unit of power is diopter. Correct? Of course, after this, we have two important topics that we will do in part 2. One is called simple microscope. Watch repair glass they'll be using. Small object you want to magnify, you can see that simple microscope. It is a lens, nothing. Microscope means microscopic lens. Correct? Compound microscope. So simple microscope working, compound microscope working, we will see in the second part. Okay, ma? So overall, we have seen about the chapter light, reflection in its properties, refraction and its properties, then loss of reflection, loss of refraction. Almost in all the exam, they will ask this question. Total internal reflection. Total internal reflection. Then we saw dispersion of light, splitting up of white light into constituent colors. That is called as dispersion. So these are the information. Then about lens, we saw convex lens, concave lens. Convex lens and concave mirror property is same. Then lens maker's formula we saw. Finally, power of a lens. Okay, Mama. So we'll continue next chapter in the subsequent days. Thank you.